Okay, so in engineering we need to work with different materials, and we'll have a look at how this relates to the physics topic of materials as well. I want to introduce two new concepts to you, which is stress and strain, okay, also known as tensile stress and tensile strain. Where that word tensile comes from, this is when an object has forces applied that are stretching. Okay, so tensile refers to stretching an object due to force. Compressive forces are when something is being squashed. Okay, so let's take a cylinder, let's say it's a wire, and let's say it's a wire of uniform cross-sectional area. Now the way we check the cross-sectional area is we'd use a micrometer, we'd measure the cross-sectional area in three different places by taking the diameter, using the micrometer, and then we take the average. And it's a reminder that for the area we would use A equals pi d squared divided by 4, which will give you a result in meters squared. A reminder that a micrometer measures to 5 decimal places within a metre. Okay, we'd measure the original length using a vernier scale or using a ruler, and then what we would do is, if the object was to extend after applying a force, we'd also use a micrometer or vernier scale, and we'd use a fiducial marker in order to compare that to its original length. Okay, so if you apply a force, okay, then what's going to happen is the object is going to extend, it's going to stretch. Okay, now the new concepts for you are stress and strain. So the tensile stress applied to an object is the force divided by the cross-sectional area. Okay, and it's important that you write it out as cross-sectional area and not shorthand like I've done here. Okay, area is a vague term, you may be referring to the surface area, for example. Okay, you've seen the equation force divided by area at GCSE, it's the equation for pressure, therefore units are pascals or newtons per metre squared, either are acceptable. Okay, the object will also undergo strain, and what this is a measure of how far it extends in comparison to its original length. So something, for example, that's a brittle material, such as glass, okay, what would happen on that strain is it wouldn't extend very far before it breaks. So you have a very steep gradient on a stress-strain graph because you don't get extension when you apply forces to glass. Okay, because it's meters divided by meters, they cancel each other out. Tensile strain has no units. Okay, so stress, force divided by cross-sectional area, strain, extension divided by original length. So let's have a look at a stress-strain graph. Okay, if you apply a force to an object, the amount of stress will increase, and the amount of strain will increase directly proportional to that. At some point, okay, when the object starts to deform, then it will no longer be proportional. In engineering, when we are building things in manufacture, the engineers and the construction people will need to know what the ultimate tensile stress is. And that is essentially the amount of stress an object can take before it starts to break. Okay, which is the peak of this graph here. What will happen eventually is the graph will break, the material will break, and then the graph stops. So, in comparison, if we were to have glass, okay, strain is very, very small area, it can take a lot of stress, and then it would break. And that's what glass would look like, and glass is a brittle material. So, these are the equations you need to be able to use, and this is the concept of stress-strain graphs, before we look at Young's modulus next time round. Thank you.